Let me go through this. First of all, the frequency is 10 megahertz, not 9 gigahertz. All right, so 10 megahertz, not 9 gigahertz. And it's vertically polarized, normally incident, propagates in the z direction, is normally incident on the material with sigma at 0.1, epsilon relative 3, and mu relative 1. Reflected electric field has an amplitude of 20 volts. Determine the following. So it's kind of a problem. I didn't make it a shield with a certain thickness or anything. This is a simple problem, a reduced difficulty problem. So the first thing you have to do is get eta 2. So eta 2, or eta in the region things going to, is j omega mu naught, mu relative is 1. Omega is just 2 pi f, and it's divided by sigma, which is 0.01, plus j omega epsilon relative epsilon naught. I'll make one comment. What I do always, and if I had a calculator I'd do this, I would create an omega variable so I don't have to keep on punching 2 pi. The more strokes, keystrokes you use, the more likely you're making a mistake. So I get eta 2. Now that's the magnitude of eta 2, and you don't just take the real part. To get the reflection coefficient, it's eta 2 minus eta naught. That's where you're coming from, is air, and eta naught's 120 pi, over eta 2 plus eta naught, which is this value. Now you notice you can't just take the minus 0.669. It's the magnitude. So once I have the reflection coefficient, I know the incident field times the reflection coefficient, I'm right here, is equal to actually the reflected field. So if I take the reflected field over the reflection coefficient, I get the incident field magnitude. That should be the magnitude. So anyway, I get the incident field. Now once I have the incident field, and so the reflected field, and I think in class we had a chuckle about it, but I try to warn you, it's as obvious as reading the problem. All right, so then the magnitude of the reflected power. Now this is reflected, that's in region 1. Magnitude of the reflected power is just 1/2 magnitude of the reflected field, which is given, squared, divided by eta naught. And that's the value. All right, the transmitted electric field. Well, E transmitted, you can get the transmission coefficient, which is 2 eta 2 over eta 2 plus eta 1. Or you can just take 1 plus the reflection. Either one is the same value. Then if you multiply the incident electric field by the transmission coefficient, you get the transmitted field's magnitude. The only thing I cared about is magnitude. All right, now I asked for the magnitude of the transmitted power density. There are two ways to do this. I took the easier. If you have the incident power density and you know the reflected power density, if you take the incident power density minus the reflected, that has to be the transmitted. That's one way, and that's down here, right here. P transmitted is P average incident minus P reflected. Or you could take 1/2 the magnitude of the transmitted electric field squared over the magnitude of eta 2 times the cosine of the angle associated with eta 2. And the answers are identical. You can do it either way. It's easier if you got P incident and P reflected, just subtract. So here we have two different antennas. For this one, I've got a 100-volt source, and I give you the impedance of the antenna that's transmitting, 73.2 plus J, 42.5. First thing, I'm going to get the current. There was no series resistance, so it's just 100 volts over the magnitude of Z antenna. All right, once I have that current, which is right here, I need the magnitude of that current. Now I need the total power radiated. That's 1/2, and it's 72.2. 72.3 would be fine, but I clicked the 72.2. It's very close. It's 1/2 72.2 or 72.3, which is the radiation resistance, times I squared, which would be about this, actually 51. That's total radiated power. Then to get the average incident power, you have to take P radiated 4 pi r squared. R is 80 kilometers. That's the average power density that would be there if it was isotropic. Then you multiply by the gain. I made sure I kept that at 90 degrees, so the gain is just 1.64 for that dipole. So now you get the power density on this second antenna. Now this second antenna has a different set of characteristics. That it has a gain of 40 dB. 40 dB is 10,000, right? It's 10 to the 4th. 40 dB is 10 to the 4th. 30 dB, 10 to the 3rd. 20 dB, 10 squared, and so forth total. So this is going to be a gain of 10,000, not 40. And there's the antenna impedance, 80 plus J20. Well, 80 is the radiation resistance that you're going to use to calculate VOC. So I'm going to assume you got an average power density here. All right, this is a wave. It doesn't matter where it came from. And it's normally incident, so there's no angular problem. And now I have an antenna here. And this antenna has a given aperture. And the aperture of this antenna is going to be lambda squared over 4 pi times the gain of that antenna. Well, that's lambda squared over 4 pi times 10 to the 4th. And lambda is C over F. C is 3 times 10 to the 8th. F, what was F? 8 gigahertz. So you can calculate that. That means the power received is equal to the average power density times lambda squared over 4 pi times the gain. And once you have this, you need V open circuit. And V open circuit is simply a square root of P received here, which is that. Square root of P received times 4, but it's times the radiation resistance, R rad. And you can see R rad for that antenna was what? Because remember, Z antenna for the second one is what? 80 plus, isn't it 80 plus J20? The real part of the antenna impedance is the radiation resistance. And that's what goes here, 80.
And where is that V open circuit coming from, that equation? P
Do
received.
you remember when we found the equivalent circuit for the second antenna if incident power's on it? When you have an antenna, we're going to model it. We know we're going to get P received. That's what's received by the antenna, period. That's the aperture catching. At most, you can only use half of it. So you can say what this looks like is an open circuit voltage here, and then it's in series with the antenna impedance. Well, the antenna impedance has got, let's call it R antenna plus JX antenna, right? Now that's all internal to the actual antenna, right? Remember, we're trying to get an equivalent circuit for the antenna. This is external. Now I can say that, this is basically all internal. This is the antenna itself. It's got some open circuit voltage in series. It's a Thevenin equivalent with some impedance. Now you got a load. Well, the maximum amount of power you can get out of this system is when the load itself is the conjugate of the antenna impedance. So when this is equal to R antenna, I'll call it R rad. Actually, the book does call it R rad, and I've been calling it R rad, so just call it R rad. And this is going to be R rad. And this is going to be minus JX antenna. Now this is just to find V open circuit. This is to get maximum power. If the antenna has impedance, real plus J imagine, JX, the conjugate would be R minus that, right? J, it's called the conjugate. We're not putting a load on, we're finding VOC, right?
Ah, okay.
This is a Thevenin, you don't know, remember Thevenin equivalent, what'd you have to do? You remove the load, right? You found the V open circuit across anything that you want a Thevenin equivalent. Then what do? You find the internal impedance. You short the source out, right, and you look at the internal impedance. So to find VOC here, what you realize is this. The imaginary part's going to cancel, so that means this current here, I, if it is matched, I itself is going to be VOC over, and it's going to be 2R rad. Now, if that's the current, this is the total power. Well, the power that would be actually delivered there would be 1. P received, that's to everything now, be 1/2, right? Squared, right? So it's VOC over 2R rad squared times R rad, right? Only real stuff can dissipate by. And actually, it's what? It's not R rad, it's 2R rad, right? Because there's 2 resistors. Okay, so what does that come down to? 1 over 4 R rad VOC squared equals P received, or VOC is equal to the square root of 4 R rad times P received. The square root of 4 R rad times P received. All right, so what's going to happen now? I got VOC, so what do? Everything stays the same. What do you do with the Thevenin equivalent circuit when you have it? Now you replace open circuit, right? Once you got that, and then shorts. Now you put the load on. The load was 50. So this is 50 ohms. I wanted the voltage at the load. So how would you get the voltage at the load? If you knew V open, what is V open circuit? 611 microvolts, that sounds right. And what's this voltage going to be then? You're going to get it by doing what? Voltage division. You got a single resistor in series with a bunch of impedances. So take that resistance, divide it by this resistance plus that resistance times this, and that will be your V load. Once I have V load, how do you get the power? It's pure resistor. Isn't it either 1/2 I squared times R or 1/2 V L squared divided by the resistance and load. Either one will do it. So this right here is just going to be equal to 1/2 magnitude of VL squared divided by the resistance, or 50. And that's true. Now, if it's at an angle, you probably get something at an angle on the final. Almost guaranteed it won't be this easy. So you might have an antenna like this, then an antenna like this, but it might be tilted maybe in an odd direction. You follow me? I'm not going to give you this tilt angle stuff where they're not aligned for maximum gain. But if you're up here and this one's tilted differently, then you have to figure out the effect on gain. Y'all follow me? You're going to get Doppler again for sure now. But this time it's going to be a little different. It won't be quite this easy. Right here, plane having a radar cross-section of 10 meters squared is flying at 500 meters per second. A 30-degree angle to the radius vector from the radar. The radar transmits 10 kW at a frequency of 9.4 gigahertz and has a gain of 30 dB. If the plane is at 10 kilometers away, determine the following. The power received back at the radar. Now you can do this several ways. Probably the easiest way is just P received at the radar divided by P transmitted, but you could also calculate the incident power density right here, just like we did for freeze. Multiply the incident power density by the size, the RCS of the object. Now you have the total reflected power. Then divide that by 4 pi r squared. Now you have the power density back here. And then if you multiply that by the aperture, which would be lambda squared over 4 pi times the gain of that antenna, now you have the power received. So you could do it that way. And in either case, it doesn't matter how you do it. If you just want P received over P, or just say you got P transmitted, I think I give you what the transmitted power is. So take P transmitted, then it's going to be times the gain of the transmitter, gain of the receiver. They're the same, so gain squared. Then it's going to be times lambda squared. Then it's times the RCS. The RCS is usually symbolized by sigma, but I put in RCS so you know. Then it's divided by 4 pi cubed, and then r to the fourth. R is the distance separated. That should be power received. Now you can do it by calculating the power density right incident here, which is transmitted power over 4 pi r squared times the size of the RCS, that's the total power reflected. Divide that term by 4 pi r squared again, because it comes back here isotropically. Then multiply that by the gain here, which is lambda squared over 4 pi times the gain of the receiver. And that will be the power received. Either one will get you, they're the same. This is a more compact form. The gain was what, 30 dB? So 30 dB is what? A gain of 30 dB is going to be 1,000 or 10 to the third. 20 dB of gain, this is all gain, power, is going to be 10 squared. 30 dB of gain is 10 cubed. 40 dB gain is 10 to the fourth, and so forth.
I'm just confused as to where you get the 4 pi. Why is it cubed?
So we got a transmitting antenna, we got a target, right? This has an RCS, correct? Let's assume the transmitted power P trans, right? Comes out. Incident power density right here, PAV, is going to be equal to P trans, or just PT over 4 pi r squared, right?
Yep.
Now we're going to multiply that by the RCS, which RCS, right? Now that's the total reflected power, right?
Okay.
Now we're going to divide the whole thing by 4 pi r squared again. Now that would be the power density back here. Then you got to multiply it by the gain. What's the gain? Lambda squared over 4 pi times the gain of the receiver, correct? And this should have a gain here too, right?
Oh, so you got to multiply it by the aperture of that.
Absolutely,
antenna,
that's the only way you can catch energy, right? If you're looking at an antenna as something that's catching energy, or more or less scavenging any energy from the environment, you have to have the effective area of that antenna. That's why there's 4 pi cubed. The round trip time, now because you know it's moving at the speed of light, and how far does it go? It goes out and back, so 2r divided by c would be the round trip time. The Doppler shift, so the whole idea is you need the component of velocity and direction. So if this is going 500 meters per second, but there's a 30-degree angle, you have to take cosine of 30 degrees times that 500. So it's 0.866 roughly times 500. Once you have that, Doppler shift is just going to be equal to 2 times that velocity over the wave. Right here, 2v over lambda times the cosine of the angle. It should be about 27.14 kilohertz. And the fourth one was a standard waveguide problem. You got two lowest frequencies. Remember, for it to be in only one mode, you can't get into the next mode. So there are two possibilities. The lowest order mode is TE10. And you get that straightforward right down here. Really, you can just look at one. Largest dimension, and that's half a wavelength. And if you know that, you got the lowest order frequencies. FC10 would be C over 2A, and I got 6.562 gigahertz. Now the FC20, which is the next normal mode that comes, is going to be twice that at 13.12 gigahertz. And that's what they always make sure of, is the next mode will be the 2.0 mode, PE, not the 0.1 mode. So you got these two. This would be the lowest, this would be the upper limit on the single mode operation. Twice that frequency. So then I ask you the impedance at a frequency right between the first and second. So you just average them and you get 9.843 gigahertz. And that impedance requires you to calculate K, which is the square root of 1 minus quantity FC10 squared over F squared. So that would be K, roughly 0.745. And because it's a 1 it's a TE mode, it's always the impedance, the characteristic impedance, it's air filled, eta naught over K. I will give everybody 3 points of raw score on your test. I'll curve it. I don't do this. I give you a lot more points than that usually for problems if you miss them. And that way, about as fair as I can think of. You recognize there's a MATLAB project, right? What you need to do is submit something that is unique. Now, this is for an ABET accreditation, and I have to have this from you or you're going to fail. One guy not handed a project and he failed. And I hate to see that. So you have to hand in a project. There's no exceptions. This is a must. It has to be on something related topically to electromagnetics. For instance, a lot of people like the shielding problem. I'm going to have multiple shield. I'm going to have a shield that has multiple layers, and what I'm going to do is design the shield using steel and copper and something, so the weight is going to have this maximum amount of weight, per cubic or square foot of surface area, and it's going to have this amount of attenuation. So they work on the thicknesses, they get multiple bounces. Remember, the density of steel and copper is different, and the attenuation coefficient. Thing is, with 1045 steel, it has a mu relative of 1,000, so it attenuates much faster, and it's about the same weight, so it's a preferred thing. Anyway, they figured out, you can figure out a way to get, say for a 3-layer shield, how to get the thickness of the shield and the materials to maximize the attenuation and minimize the weight, or say you get an attenuation of, say, 70 or 80 dB, and over a frequency range from like 5 to 10 gigahertz. Start with 5 gigahertz. That's going to have the max. That's going to have the minimum attenuation with a minimum weight. It's a great problem. It takes some thinking. You write up a code, you do it. You have to come up with an idea related to electromagnets that would have some value to society that is unique. Because what people do is they go to Google and they'll look at prior projects. They have this crazy algorithm that it catches plagiarism. So anytime a project is similar to other people's, it'll flag it and show you what it is. And if it looks too similar, you get in trouble. I don't do that, but they do that. Somebody else looks at the ABET crap. So here's the deal. Find something unique. Just be honest with yourself. I pretty much green light everything. Here's something. You got an antenna that's a dipole antenna, and you want to transmit through a wall to the other side, and you got another antenna over there, and you got to come up with some electromagnetic model for the wall. That you can look up on Google. You can look it up, but you can look up all sorts of things for the wall. This is EMC. And you want to do something over a frequency range. So what's the minimum power to get, say, a fairly good footprint on the wall using a type of antenna that would do it? That would be basically a loop antenna or a short dipole.
What do you mean we got to use MATLAB to code it?
Because that's what it takes to do these problems. You can't do them by hand. You're going to have something where you're going to do a simulation.
How do you do simulations?
A MATLAB? You're supposed to be familiar with MATLAB. I'm told that directly. Have you run a script on MATLAB ever?
I think we did it in our basic signals and systems lab.
It's not this though. We made a square wave.
I mean, if you want to do it with Python, go ahead. Or if you want to use, do you want to use C? Which language do you want?
I'm just trying to understand, what do you mean, we have to use a MATLAB simulator tool? Because that's, my buddy had a simulator tool on MATLAB.
Well, you can do that if you want, but you know,
is it just a code?
All right. Suppose I have a dipole antenna with a length of 0.485 lambda. I don't want to make this hard. I'm trying to just show you. All right. Then I have a wall. Now, the wall, electrically model it. Let's make it real simple. Suppose the wall is going to have something where, say, sigma of 10 epsilon relative of 5 and mu relative equals 0. Make the wall 1 meter thick. That's probably an oversimplification, but it'll work for proof of concept. Now over here I got another antenna, and here's a load. Got a range from here to here, R. Make that 30 meters. Again, I'm just coming up with numbers, right? Make this range 10 meters. Now what I want to do is write a code so I can figure out for any given frequency how much power from here will get to here. So there's a couple assumptions you have to make. The first assumption is you're going to look at the direct line path. It's going to go straight through here to here, assume they're in line, and that's it. If they're that way, what I need is the power density right here. I need PAV, and I'm just going to have right here, right at this point. We're going to move and start getting the power density at different heights, all right? And it'll be at a different angle. That will be a reflection coefficient you have to enter in. So let's go ahead and do it. This instant power density, I'll call it PAV1 right there. And I'm just going to say this has a certain amount of power. It's transmitting PT, okay? I'm assuming that. So I assume PT, that means the average power density at the wall, PAV1, would be equal to PT over 4 pi R squared. And that's 30, but I'll call this R1. R1 squared. Now that's the power density right here, right? Now what do you really need? I need the power that's coming out this end, P transmitted, right? Isn't that what I ultimately want? So how do you get that? Well, you can make some assumptions here. You can assume I'm only looking at this with no reflections. I'm not looking at multiple reflections. If I'm not doing that, what do I need to get this? This would be a great question for the finalist kind of.
Use freeze. Or you could use it like a shield.
Right, what would you do?
You find 2 towels.
How about we do it this way? This is the average power density right here, but I need to multiply it by the gain. If that was a half-wave dipole, it would be 1.64. It's normally incident. Do you agree with that? All right, now if that's the incident power density, let's get the incident electric field. That would be what? 1/2 magnitude of the incident electric field there squared over 8 Could we get the incident field? Here's where another assumption comes in. So the incident field would be equal to 2 8 times average power density in region 1, and it would be the square root of this. So now I have the incident electric field right here. It'll be easier for you to see it this way. Now, what I want is this, but what I'm going to do is get something that's very critical to this. What do I need to figure out the reflection, transmission? Do you agree with that? Once I get it in there, what happens? Then it exponentially decays as e to the minus, because the only thing I care about is magnitude, right? So then it exponentially decays in here as e, whatever it amounts to, as e transmitted. And that is proportional or equal to, better yet, some value k over R2. Here's what I'm really saying. You're assuming as this is going out, the reduction in the field value after that point is going to be like a spherical wave that normally falls off as 1 over R. So if you know the value here, and that is at a range of R2, you can say K over R2 is the transmitted field value. That means you can say that K itself is going to be R2 times the actual transmitted field value. Now this is a little bit beyond the scope of this class, but this is the way the problem would be done in EMC. That means the field, when I'm all the way at R3, the electric field at R3 would be this value K over R3. And here you can see it's a proportionality. So therefore, R2 over R3 times the transmitted field at R2 would be the field at R3. That's how you get the electric field incident. From that point on, you could get the effective area there. You could get the power density, couldn't you? You could get the effective aperture of this antenna. You could get the open circuit voltage. You could model and you could get that. So now we've got a set of equations that go from transmit to receive. And what I want you to do, if you did this, is you want to see something about, say you get curves, you want to find out if you're exactly 10 meters away, maybe how thick this wall could be before you get a voltage level below, like 20 nanovolts or 20 microvolts. You all follow me? You set some parameters, then you have to model it and you'll get curves. You'll say voltage on load versus frequency, or voltage on load for a given frequency versus thickness. And you get what are called family of curves. And what it's showing you is you did a proper scientific investigation of the phenomena, and based on that, these are your conclusions. Now the MATLAB's perfect for this.
So you don't model it, you just build it. Or
That
if
is
you
modeling.
do model it, you don't build and test it or anything.
You don't, well, if you want to build it, have at
Oh,
it.
that's
but-
what I was kind of like,
No, you're not going to build
I was
something.
about to say.
You're not going to have to fabricate something, but you're going to model it. But MATLAB's perfect. If you've not used MATLAB for it, I promise you there's a cajillion things on YouTube and other places that'll show you how to program. And if you need help, I can give you some stuff with Dr. Winters. The whole idea is this: if you have equations on paper. Now remember, what we want to do, you want to get something where you can increment things, frequency, thickness. So you get families of curves and you make decisions based on the output, families of curves. I can show you a beautiful thing with radar operating curves too. If somebody's interested in radar, come see me. But just think for a bit about something of interest to you. People have all sorts of interests that are crazy. Some of these people they want to communicate, I don't know, in areas without cellular transmissions, and they want to use different antenna platforms, and they want to know, what they're going to do is investigate which will give the best ground coverage based on a location of a transmitter. All those things are legit. Some of this stuff is over your head. Find something you're interested in, come see me and let me green light. I got a lot of weird ones last time. If you have problems, come see me, I'll give you one. But I prefer you to come up with one. And send me an email with what you plan on doing. Give me 3 or 4 lines, and then when I green light it, say it's okay, go ahead and do it. If I say no, come see me, then see me and I'll adjust it or do something, all right? I'd start on it sooner than later because we got, 2 weeks left?
So when is this going to be due? Last day of class?
Last day of class.
It's a paper submit? How's?
Well, you have to show me your MATLAB code. So you're going to have to run your MATLAB code for me. Unless it's Python, then you run your Python code. You got to run the code to show me it works. That's first. And then you write it up. I didn't used to do this, but I tried to run people's codes, and I found that they're just lying. None of these codes work. So you're going to have to show me that it works. So, because I'm telling you, you won't believe what I get. Then make sure it works. See me, and then show me the plots. Give me the code. Show me the plots, and then you'll run it.
It's like write a paper, a report.
You describe it in maybe 4 pages. It really doesn't have to be that long, but it's really something to check a box here for the ABET, but it has to be unique. And those guys, I have never had any bad feedback about the projects I passed and stuff like this. But you know what ABET is? It's an accreditation organization. And if you aren't ABET accredited as a program, you're going to have a hard time getting a job, basically. Federal funding and stuff like this is very important. So what they'll do is they'll come and they'll take a look at people and the projects. And some guy who's from another university typically is evaluating to see if these projects are representing the difficulty and challenge that they want to see. And if they're not, they put a question mark and then you get in trouble. I never got in trouble with them. That's what I'm telling you.
So like 3 pages of figures and 1 page double spaced words.
Let's think about how you would want to do this if you were trying to do it for a boss. All right? Think of something. You got to have a discussion about it. Show the code. This is of interest to me. Define the problem. Here's the solution method. Dictate it. But the whole idea is this: just do it right. Think of something of interest. Don't try to get away with anything. Discuss it. If you don't understand how to do the next step, come see me. I'll try to help you. But it should be something you learn from too. I didn't make up this rule. ABET did. I thought it's insane to have kids come up with the ideas for their own project. Bosses don't do that. Bosses tell you, this is what I want you to do.
Yeah.
Until you're in grad school, at least, and then you have to do a PhD dissertation, you have to come up with the idea and you have to come up with the solution.
What are they?